Section 5.1, we're going to take a look at addition and subtraction of integers. We're going to look at models, methods, ways of explaining to students why things happen the way that they do. Integers show up in 5th to 6th grade is usually the first time students encounter this idea. And they continue when you look at positive and negative values with variables and things like that all the way through junior high and high school. So this is a concept that starts pretty, early in all of those kinds of things, but it continues on for quite some time. So to start with, integers. Your book uses the letter I to reference them. Most books do not use an I, they use a Z. And if I'm remembering right, it has to do with the Latin word for integers. But the reason most resources don't use an I is because there are other vocabulary words with I's that we could use I for. For example, irrational or imaginary. There's 3 options. So if I write down I, how do you know which one I'm talking about? So Z is a more common word notation for our integers. I'm going to write the set notation for integers. A set notation for integers, we've talked about them before, is that it's the positive negative whole number. So we put the ... at the beginning, and I'm going to do -3, -2, -1. It does include the number 0, and then 1, 2, 3. And then we'll put a ... and we'll keep going. So everything we did back in chapter 3 was all about whole numbers. And now this actually creates for us the positive and the negative whole numbers, in essence. All right, there are 2 different models for integer addition that feel almost the same. They have some slight variations, but they're very, very similar. And these 2 models are called the chip model and the charged fields model. So if you have something besides just whatever writing utensil you're working with right now that's a different color, go ahead and grab it out right now. If not, you can do things as hollow and filled in solid. That's fine. But if you have a couple of colors, it would be useful. What we're going to do is we're going to pretend like we have poker chips, which actually have color, right? So they're usually lots of different colors, but some real basic plastic ones that you can buy are reds and blacks. Those are often really good ones for what we're talking about, and the colors that I'm going to use are in fact going to be red and black. Let me actually set that up real quick. Okay, I think that'll work. So our positive chips are usually done in black. Okay, you can pick whatever color you have that's closest to that idea. And then our negative chips are usually done in red. And the reason that they're done that way is that when you see most things done in spreadsheets, people will talk about black being positive and red being negative. You'll hear phrases of I'm in the black or I'm in the red. In the black means that you have a positive value like in your bank account, right? That's a good thing. In the red would mean you have a negative value in your bank account. So black and red are very commonly used, but if you use a different color on me, that's fine. Just let me know what you're meaning by your pink or your green or whatever you're using, okay? Another way to do this, if you were to use poker chips, and I've seen, and it's actually really helpful too, is to take the chips and to actually, whatever color they are, like maybe you have a bunch of white chips already and you're not going to go buy more chips, right, to use in your classroom, and to use colors to actually, like Sharpies or maybe a colored piece of, like a sticker, to designate the difference on either side. So one side's positive and one side's negative so that students can use the chips interchangeably. That's an actual way of doing it. So if you were doing this in a real classroom, you would have chips. And maybe your school doesn't want you to buy chips, but you know what? You can get some colored paper and you can do the same thing. They don't even have to be circles. Don't make them look like chips, make them look like little squares because it's easier to cut out. It doesn't matter. But it is really nice to have one color represent a positive and one color to represent a negative. So what you're going to do is you're going to start out by drawing a circle. And inside your circle, you're going to put 5 positive chips. So for me, that's 5 black chips because my black is my positive. And then you're going to do 3 red chips because it's a -3. That's what it's going to be on my picture. Yeah, 5 blacks, 3 reds. So let me actually write that down. So for me, my black, whoops. is positive, and my red is negative. Okay, everybody good with the picture so far? All right, so the idea with this picture and the idea that your students would do is they would actually take a black and a red at the same time, and they would remove them from the circle. And when we do that, it's called a zero pair. A positive and a negative combined cancel one another out. They add to zero, they balance one another. Whatever language it is that resonates, use that. And the idea is that they occur in pairs that can be removed. So I have a black and a red here that get removed, a black and a red here that get removed, and a black and a red here that get removed. And once I do that, once I do that, I have left 2 black chips in my circle, which represents the number positive 2. Okay, so far so good? Okay, so the nice thing about this model is it's super hands-on. We always like those opportunities that our kids have to be able to actually do the math with their hands, right? Kinesthetics, stuff like that. Anything that we do using more than one way of learning sticks a little bit better than we just stick with one way of learning, so that's really good. Obviously, we're not going to do this eventually when we end up with bigger numbers. I mean, we're not, right? We're going to use other methods, but to concretely understand why they're balancing each other out, this works pretty nicely. Let's take another example. Okay, so same numbers, same circle. In this model, you're not using any colors, you're just using one of your, whatever you're writing with normally. And a positive, when I draw a positive, is going to, like a plus sign, it's going to represent a positive number. And if I draw a negative, it's going to represent a negative number. So in my diagram, it says 5, which means I'm going to write 5 plus signs. And it has 3 negatives because these are charges. It's a positive and a negative charge. Now, if you're thinking in terms of batteries, things like that, a positive charge and a negative charge cancel one another out, right? They're a charge issue. They cancel, they balance, they're a zero pair. And the same way that we did the last time, we remove all of the zero pairs. And the result when we're done, of course, is 2 positives to give you the number of 2. Okay, very similar, a little bit different language, a little bit different tactile learning kind of stuff, right? Like there's no tactile learning here, but there's definitely this idea of charges involved, which resonates for some students. Number line. You ready for the next one? Okay, so imagine doing this in the classroom where you put tape on the floor. So not only are they moving things around with their hands like they were back in the first one with the chart or the chip model, they're actually moving their whole bodies. Okay, so I'm going to show this to you with the desks. So we're going to let this desk right here in front of Danielle be our starting spot, and it says positive 5. So I'm going to move forward 5 desks. So I've got 1, 2, 3, 4, 5. And then the negative 3, I'm going to go back the other way, right? So I'm going to go 1, 2, 3. And then what happens is I look at how far I am away from where I began, and I'm 2 desks away. So the answer would be 2. Okay? So the kids can get up, they can move, but then we want to actually be able to show it on a number line on the paper too, and we can do that next. So the next part to do on this one will be to show it on the paper. So we're going to draw a number line. We're going to mark that we start at 0 at the beginning. And then we're going to move 1, 2, 3, 4, 5. You can do individual hops if you want, kind of like I did as I counted along, or you can just draw the arrow representing that I went all the way over here to 5. I'm okay with that. And then the negative 3 means I'm going to go backwards 3. I used colors just so that you could see it easier on my screen, but you don't have to use colors. So I moved backwards 3, right? And the question is, where did I sort of land or end up at? And the answer, of course, is 2. All right, we good? I think it's just one more. Yeah. One more. One more method is called a pattern model. Generally speaking, the pattern model does not resonate in this classroom when I tell you guys this. You look at it and you're going to be like, why would you do it like that? And I understand that. But as always, remember, you're not teaching you in a classroom. You're teaching a whole bunch of other kids with a whole bunch of different life experiences and challenges and abilities and different kinds of things. A pattern model tends to work really well with people who do and think in patterns, who do patterns, see patterns, think in patterns. A lot of your kids who might be special ed with some autism, right? Autism or autistic tendencies sometimes resonate with patterns. It's one of those things that really resonates with some of those kids. So this is an interesting approach, a little different. So let me show you how it works. The idea of this approach is to create a pattern that we know something about and to start with numbers that we know something about. For example, 5 plus 2. I know what 5 plus 2 is. It's whole numbers. I did it back in chapter 3, right? Yeah. So what is 5 plus 2? It's 7. And we're going to keep the 5 the same because it matches the 5 that eventually I'm going to want over here, right? So let's try 5 plus 1. And that would be 6. And we're going to do 5 plus 0. And that would be 5. Okay? So what we notice is that if you look at the right-hand side of this, there's a pattern, right? 7, 6, 5. If I continue in the middle ground here with taking 1 away each time or doing 1 value less on a number line right through here, I expect the numbers to go down sequentially on the right-hand side as well. So, for example, if I write down now 5 plus negative 1, looking at the pattern that I've established in green, I expect that number to be 4. And if I do 5 plus negative 2, looking at the pattern, I expect this number to be 3. And if I look at 5 plus negative 3, with my pattern, I expect this number to be 2. Okay? So if nothing else, what this does is it really does justify for us that a positive 5 plus a negative 3 ends up in 2 in 4 completely different ways. Chip model, charged fields model, number line model, and patterns model. All right, we're going to shift gears just a little bit and take a look at a related topic. It shows up in our section called absolute value. An absolute value of a value is actually a distance. And because it's a distance, it's always a positive number. So when you take, for example, the absolute value of 5, well, that's a distance of 5 back to the original number 0. Think about a number line. But if I had gone negative 5, well, if I'm at negative 5 on a number line, the distance back to 0 is still 5. Okay? Absolute values are simply the distance back to 0, and it ends up being all positive numbers. If you take a look at the definition, it kind of doesn't look like that's what it's saying. It kind of looks like this negative here might be misplaced. Do you get that feeling? It's not, but it looks like it. So let me explain what it's doing. In the first scenario, it is what you would expect. The absolute value of x is x. But the condition here at the end tells you why. These are values that are bigger or equal to 0. So if you have a number bigger than or equal to 0 and you take its absolute value, it doesn't change. But on the second one, these are numbers that are already negative. So this number in here, while you don't see a negative, it is a negative number. So let's say, for example, that this number is my negative 5 that I wrote below. How do I do this? Well, what this definition says is that I need the opposite of the value that's in the absolute value symbols, negative 5, which would give you a 5. So if you'll write on your notes here that this negative is sort of basically best understood as being the opposite of. So when I take the absolute value of a negative number, I get the opposite of that negative number, which ends up being positive. The reality is that we're a little bit limited because the notation in mathematics doesn't give us a better choice here. My negative simply has to mean the opposite of when I think about it from this context. So let's take a look at a few examples involving absolute values and how their signs are. So the issue with absolute values is never about the value, it's always about the sign, right? The values are going to be what they are. That never changes. It's just the sign that we have to be careful of when we're thinking about it. So on the first one, is that the directions say classify as true or false, and if it's false, show a counterexample. So the absolute value of x to the fourth is x to the fourth. Well, always we have to decide if what's inside the absolute values is for sure positive, or if it's for sure negative, or if it's some of both. What do we have? So what can you tell me about the x to the fourth? What kind of number is x to the fourth? It is positive. How do you know? It is an integer, but we have negative integers too.
I mean, it's inside the...
I'm sorry, maybe I'm not asking the question right. Let me try one more time. I don't care about the absolute values. I just care about the part in red. Just the x to the fourth part. Okay?
It can't be negative because even if x was negative, if you multiply 4 times, that would cancel each other out.
Okay, did you guys hear? This is saying no matter what x itself is, I'm going to multiply itself 4 times. And when I multiply something an even number of times, in this case 4 times, all the negatives cancel out. So I for sure have an absolute value here that the inside of it is positive. So what that tells me is I'm sort of on line 1, my top pink line here. It is for sure a positive number. So is it acceptable to simply remove the absolute values? Will those be equal? Yes, they will. So this one's true. And you can jot yourself even a note if you will. It's true, just so you know, because x to the fourth is always greater than or equal to 0. It technically could be 0 if x is 0, but it's definitely not negative. How about on B? Yeah, that power is odd. So could it be negative? It could. So this one is not always true, which makes it false, at least some of the time. So it's false, and then we needed a counterexample. So somebody give me a negative value for x. Negative 2? Is that what you said? God, okay, good, negative 2. So if I took negative 2 and I took negative 2 to the fifth, what would I get? Yep, 32, and it'd be negative, you're right. And then the absolute value of that negative 32 would be 32, right? But that does not equal negative 2 to the fifth, because it was negative 32. Right? The value underneath could be negative in that scenario. So I can't simply remove the absolute value symbols. The absolute value of x is not negative. Is that true or false? That is true. The absolute value of x is positive. It could be 0, so it's false, yeah. So this is false because it could be 0. All right, we're going to write down our properties of integers really quick, and then we'll be done for today. We have seen almost all of these properties before. In fact, the 4 that are listed on this page, Theorem 5.1, we have seen all of them before. The closure property of the addition of integers says that if you add 2 integers together, you get, let me say, this is a unique integer. We had that property for whole numbers. Whole number plus whole number is a whole number. Integer plus integer is an integer. I can't take integer plus integer and get a fraction. It doesn't work that way. The second one, the commutative property of addition, right? That says that when I add in whichever order, I get the same value. So it works with negative numbers just like it worked with positive numbers. 5 plus negative 2 is the same as negative 2 plus 5. Negative 7 plus negative 3 is the same as negative 3 plus negative 7. The associative property for integers, it looks the same as well. A plus B, and then I add the C, is the same as A plus, and then we add the B and the C together beforehand. So grouping doesn't change values when I add integers. And the last one, the additive identity, it's still 0. So 0 is the additive identity. Such that 0 plus A is equal to A plus 0 is equal to A. A couple things to make you aware of really quick. This homework will be due on Monday because you will finish up with a section with a video part of the second part of the section. So we'll finish it up, turn it in on Monday. Please be working redos. You can still bring those to my office either on Thursday or Friday, and I will have them back for you, 24-ish hours, whatever the next day is, in class or at my office if you want to come pick them up. And then lastly, if you choose to do section 5.1, please notice in the first part of this section, I did no content questions, right? No applications whatsoever. That does not mean if you select 5.1, you don't have to. It's not what your presentation is. Your presentation includes content questions, but you can use those methods to solve them. Okay? All right, I will see you guys on Monday.